So up to now, the materials that we considered are electrically insulating, right? Sodium chloride or potassium chloride, aluminum oxide. These are electrically insulating materials, which means that there are no free electrons in there. But you are familiar with very many metals, right? So in your day-to-day life, for instance, you handle very many metals. For instance, stainless steel spoons, right, and forks. And you're familiar with some other metals. For instance, copper is very familiar, gold is very familiar, silver is very familiar. So one thing that is common about all these materials is that they have what we call as conduction electrons, because of which they can conduct electricity, right? So in the module 3, we are going to study the theory of metals, quantum theory of metals rather. So let me start by, listing some of the properties of metals that you can recall. So one of the properties that will come straight in your mind is their ability to conduct electricity. They are very good conductors of electricity, right? That's why all the electrical wiring is done with copper wires, because copper is a good conductor of electricity. Silver is even better conductor of electricity, but because it is more expensive and tends to get oxidized, so we don't use it. So let me list it then. So the first property is that their electrical conductivity is rather good. So good electrical conductors. And we are going to quantify the electrical ability to conduct electricity by a quantity called electrical conductivity, which you are somewhat familiar with. It's the reciprocal of electrical resistivity that you measure in the lab. So we'll write down later. Then these are also good conductors of heat, right? If you have ever worked in the kitchen, try to make your tea, you would see that that on the pan that you're using for cooking, the handles are typically made of Teflon or some insulating material, so that you don't burn your hands, because the metals are good conductors of heat, so the whole vessel get heated, metallic vessel. So they are good thermal conductivity, or good thermal conductor rather. And of course, once again, we have to quantify what it means by good thermal conductivity. So we have to give we have to come up with a quantity that quantifies how good a thermal conductor the given material is. So that will be quantified in terms of what is known as kappa, which we defined in the last lecture in the context of phonons, right? So today we are dealing with kappa due to electrons, electronic thermal conductivity, right? So they have a good thermal conductivity, they have a good electrical conductivity, and that we will quantify by this quantity sigma, which is measured in the units of Siemens meter inverse, right? And kappa is measured in the units watt meter inverse Kelvin inverse, right? And then what else do you know about metals? So of course, you know that they are malleable, right? Which means that you can take a metal in some shape and deform it into some other shape, something else, without actually breaking it apart, right? So you can have, you got the point. So that is malleability. And then the metals are ductile, which is the ability to draw them in the form of wires, right? So they are ductile, they are malleable. But we are here, we are not dealing with the mechanical properties. We'll be more concerned with the electrical and thermal properties. So therefore, let me go to the next property, which is related to the thermal property, which concerns the specific heat of metals. Okay. So the specific heat. So if you take a real metal like copper, for instance, there is a lattice of copper ions, and then there are these electrons which are called conduction electrons. So, as I told you while teaching specific heat of insulators, that when we will go to metals, we will have to take this additional contribution into account. So, the total specific heat would be the specific heat due to the lattice and the specific heat due to the electrons, and it is the electronic specific heat that we are worried about in this part. So, it will be C electronic. So, we can write it as CE. CE I think is better. CE is the electronic specific heat, and you measure it in the same units, joule per mole Kelvin or joule per kilogram or whatever, right? And what is very interesting is that the specific heat of metals, it goes as T. Okay. Now, if you recall, the specific heat of insulators of a lattice, bare lattice, goes as T cube at very low temperatures. But if you start increasing the temperature, the specific heat increases very rapidly, and then it tends to saturate to a value which is known as Dulong-Petit value, which is the classical value 3R, right. So, that is the nature of specific heat of an insulator or of the lattice, C lattice, right. But C electronic goes as T up to very high temperatures, practically all the temperatures that you can access before melting the material, right. And this is something which is very puzzling, why the specific heat of metals increases linearly with temperature and for all temperatures, for all practical purposes. Of course, if you can think of, or theoretically if you can think of a metal which does not melt at any temperature, then you would have to heat it to temperatures of the order of 10,000 Kelvin in order to reach what is the classical limit, that is 3R. Okay. In this case, it will be 3 by 2R, because there are only one kind of degrees of freedom, there is no vibration. So, this is a very puzzling result, and we have to understand this in the course of this module. Then there is something very interesting, and once again it comes from the experiments. This also comes from the experiments. Actually, most of the things that we deal with here in this course, they are driven by the experiments. Okay. For instance, the metals are known to humans from a very long time, the Bronze Age and the Iron Age and so on. So, but the properties, we started explaining their properties theoretically by framing theoretical models very recently, only in 1900, that we started trying to make sense of why different materials behave the way they do, and in particular the properties of metals we started understanding from the beginning of the previous century. That is where the entire this quantum revolution was happening, right. So much before that, in fact, as I was telling you about Dulong and Petit, and in fact I sent a little note also from Wikipedia. I don't know if you read it, that one of them, either Dulong or Petit, he even lost his 3 fingers performing experiments in his backyard. So there were people like them in France and Germany. So there was this Weidemann and friends, and what they did, they measured the thermal conductivity and electrical conductivity of lots of metals in 1870s. No, I mean much before we started thinking about metals, their theory, and they found a very strange connection between sigma and kappa. Today you may not see it as very strange, because the electrical conduction happens through electrons, conduction electrons. The thermal conductivity is also through electrons. So you may envisage that there has to be some connection between the two. But in 1879, empirically, they derived a relation which is that kappa of a metal divided by its sigma, okay, is proportional to temperature, which means that this is equal to some constant times temperature. This is an astounding result. So, this constant L, this is known as Lorentz number in the current times, and this Lorentz number is fixed for all metals, and they derived this empirically by performing experiments one after the other. Maybe it took them several years to collect data on a couple of metals, maybe 4 or 5 metals or 6 metals, and they found that this is very surprising, that the measured thermal conductivity of copper divided by its electrical conductivity is equal to, at let us say at room temperature, let us say they are performing the experiment at room temperature, then T is a constant, right, 300, and then there has to be some constant which they should put in order to get this, and this constant is independent of the metal that they are choosing, independent of the material that they are choosing. So, this is called Wiedemann-Frenz law. And it is very much in use in today's research also. In fact, in my own research, I use this law to decouple the thermal conductivity of electrons from the lattice. I will come to that later on. So, our job would be to understand this in this module, that why these two are related in this manner. This is called Lorentz number, and this Lorentz number is given by, it is a pure constant. I think many of you are heavily impressed by the constants that you come across in high energy physics, but here you see a very low energy physics, the metals where the energy scale is milli electron volt. You have an astounding relation, thermal conductivity divided by electrical conductivity, independent of the metal you choose, goes by this relation, where L is a universal constant, depends not on any of the properties of the material, right. It depends on just Boltzmann constant and the charge of electron. And then we will also look at what is known as the Peltier coefficient, Peltier effect, and the Seebeck effect, right. You may have read it somewhere at some point in time. Let me remind you. So, if you take a piece of metal and you create a temperature gradient across its two ends, which means that you put a source of heat here and you put a sink here, okay, then there will be a voltage gradient that will appear as a consequence of the temperature gradient along the length of the material. Okay. So, this is TH, the temperature of the hot end, here is the temperature of the cold end, and delta T is the temperature gradient, and in response to the temperature gradient, you will get a voltage gradient delta V, and this ratio delta V over delta T is known as Seebeck coefficient. All right. But you imagine when you heat this end and this end is colder, the conduction electrons, actually this is the part of the lecture which we will deal with later on. The electrons here have more energy, they are energetically more excited. So, they move along the length of the conductor and they pile up here. So, this part becomes slightly electron deficient compared to this part. This part is in fact has more electrons. So, therefore, there will be an electric field from the positive end to the negative end, and this electric field will prevent the further transport of electrons from this end to this end. So, for a given temperature gradient, you can only get as much of a voltage difference. It's not that forever the electron will go on moving and you will keep on piling the voltage. Okay? And in fact, the metals are not very good in this. I mean, the Seebeck coefficient for metals is very low. If you want to get high Seebeck coefficient, you have to go to semiconductors, okay, for reasons that you will see during the course of this module. Okay. And then we have the Peltier effect. So, the Peltier effect is the reverse of this. In the Peltier effect, what you do is you pass a certain current through the material. So, there is a current that you are driving through the material. And in this module, our material is always going to be, invariably going to be metals. And in metals, the charge carriers are electrons. So, when you have a current flowing in this direction, actually inside the material, the electrons are moving in the opposite direction, right? That you know from your previous studies. Now, when the electron moves inside, what it does is it drags along with it some heat. Okay, so it takes the heat from this side to this side. So, this end becomes hotter and this end becomes colder. So, this is just the opposite effect. Because of passing current, you generate a temperature gradient. Because you have applied a voltage gradient, without applying a voltage gradient, you cannot draw current through the material, right, through the metal. So, you create a voltage, you apply a voltage gradient. In response to that, you get a temperature gradient in this case. Okay. And so, if you have JQ as your thermal current, okay, which I will define in a moment. So, if JQ is your thermal current and little j is your current density, the electrical current, then they are proportional to each other. Okay. And this proportionality constant is called the Peltier coefficient, which is denoted as pi. This is the Peltier coefficient. So, this is once again a remarkable property of metals, that when you draw current through them, you get a voltage gradient. So, these are some of the properties that we are going to look at, which are listed over here. Okay. So, now let me first of all, let us try to settle this question: why are there electrons in a metal that carry heat and electricity and so on and so forth? I mean, what is responsible for all these properties? What is responsible for all these properties is the electrons, right? So, where do the electrons come from? So, to understand that, let us take the case of sodium metal. Sodium is a metal, right? So, you know that sodium has 11 electrons. Of these 11 electrons, 10 electrons are tightly bound to the nucleus. These are called core electrons. But the 11th one is loosely bound, that is the valence electron. And if you remember, in the formation of sodium chloride, this electron was completely given to the chlorine, isn't it so? Chlorine took it from sodium. So, this electron went from sodium to chlorine, right? But in the case of metals, when you bring very many sodium atoms very close to each other, what happens is that this electron, it loses its connect to its parent nucleus. It becomes what is known as itinerant, which means that it moves around the entire body of the metal. Then we call it a conduction electron. All right. So, how would we picture a metal? So, to picture a metal, let us say this is a piece of metal. So, inside this piece, you have positively charged ionic cores, right, because one electron is gone, therefore, it is left with one excess proton, right. So, it is not electrically neutral. So, this is the ionic core and this is sitting at the lattice site. So, this is not moving. All that it can do is jiggle a little bit back and forth, that gives rise to lattice waves, right. But we will set the lattice waves aside for the time being. So, this is your ionic core. This is another ionic core, this is another ionic core, this is another ionic core, and there can be very many of them, of course. How many of them would be there? Avogadro's number in centimeter cube of material, right, that many. And suppose from each of these you get one electron. So therefore, you have Avogadro's number of electrons also, because each atom has given one of its electrons, right? Which is true for sodium, it's also true for lithium, it's also true for copper and so on. So therefore, these ions, these immobile ions, they are immersed in a sea of conduction electrons. The conduction electrons, these are the conduction electrons. So they are everywhere. They are all over. And the density is uniform all through. So if you take any little tiny piece of metal, it will be electrically neutral because you have as many electrons as the positively charged ion cores, right? So if you go on dividing it, you can go on dividing it, it will remain electrically neutral. So this is the picture of metal, and this is the picture that emerged in the beginning of 1900, and the first model of metals was given by Paul Drude. And this is his model. This is how he modeled it. He said that the electrons are mobile, they are itinerant, these are called conduction electrons. So his model is, let's list the properties, the main postulates of his model. So his model is that you have immobile ionic cores immersed in a sea of conduction electrons. Okay. So you can take this as sodium plus, if we are talking about sodium crystal, sodium metal. So each of these is Na plus, and the one electron that it has lost is somewhere in the metal, doesn't remain anywhere around the parent nucleus, can go anywhere. The second point is, so what do the electrons do? They are very tiny particles, subatomic particles, right? So at any temperature, at room temperature, they will have a lot of thermal energy, and because of that, they move. And when they move, what do? They collide. They collide on these ionic cores. They get scattered by these ionic cores, right? So Drude, he assumed that the electrons, they collide on these immobile ionic cores, okay, and after that, you know, after the collision, the direction of their motion will change, but the speed would not, which means that the collision is elastic, right? So this ionic core is immobile. The electron comes, it gets scattered or it collides on the ionic core, and you know, it moves this way, and then it moves this way, and then maybe it moves this way, and then it moves this way, and so on and so forth. It keeps doing like this. Okay. So the important assumption that he made is that between any two collisions, for instance here to here or from here to here, between any two successive collisions, the electron is moving along a straight line. Why? Because during this motion, there is no force acting on the electron, just consequence of Newton's second law of motion. So it moves, there is no force acting, so therefore its velocity cannot change, right? So between the collisions, the electrons move along a straight line. The electron moves. When I say electron, I mean conduction electron. Electron moves along a straight line, which can be in any direction. And in fact, if you take a snapshot of a metal, of Drude's metal, let's call it Drude's metal, then you would see that the electrons are, well, snapshot is not the right word. Let's say if you make a movie of Drude's metal, you would see that the electrons are moving in all possible manners, in all possible directions. What that means is that there is no net flow, no net current that is flowing, no net transport of charges, right? So, if you look at any point, this point will be visited by electrons from all directions. The probability that the electron comes here from all directions is the same. So, that means the average of the velocity is 0. It's going to be the time average, right? So, we assume that between the collisions with whom? Collisions with the ionic cores, the electrons move in a straight line. So, what we have basically done is we have neglected two things here. One thing is we have neglected any interaction between the electron and the ion. We assume that the interaction is instantaneous. It happens only during the collision, and all that it does is it changes the direction of motion of the electron. But once the collision is done, then the ion has no control on the electron. Now, you may say this is not correct. Well, this is just a model, right? So, you will see the weaknesses of this model also, but before that you will see the strengths of this model, and it's just 1900, right? It took us next 20-30 years to get the correct picture starting from here. So, we have neglected this electron ion interaction is neglected, okay, and this is known as this particular thing, electron ion interaction is neglected. When you neglect electron ion interaction, you call it a free electron model. So, Drude's model is a free electron model. So, this is free electron approximation. Okay. And the second thing, which is very striking, is that he neglected completely the interaction between the electrons. The electrons should repel each other, and there's a high density of electrons in the metal, right? About 10 to the power 23 electrons in a centimeter cube. But he just simply assumed that the electrons do not see the other electrons. Electron-electron interaction is neglected, and this is known as independent electron approximation. Now, you would be surprised to know that even in the modern theories, you hardly need to consider this. Now, does it not surprise you? Because I just said that electron is very densely packed with electrons. Metal is very densely packed with electrons. So, there has to be some electron-electron repulsion, right? But you would see that in very special cases, in a class of compounds called strongly correlated systems, where you see this high temperature superconductivity and other exotic phenomenon, you don't need to consider this. So, in order to understand the properties of copper, of sodium or nickel or whatever, transition metals or even more exotic metals like samarium or gadolinium, don't have to ever worry about the electron-electron interaction. And this happens because of the screening which is happening inside the metal, because there are positive ions and they screen the electrons from seeing each other. And this screening is so strong that this wins almost all the times. You don't really need to worry about the electron-electron interaction. So, even when we will go to a more advanced model, we will throw away this approximation, electron-ion interaction. Okay. We will also throw away this assumption that the ionic cores are immobile. Okay. But this will remain because this does not hurt us. This is the reality. The reality is that the screening takes care of the electron-electron interaction. Very good. So, okay, the next point. So, let me continue with this. So, this is 1, this is 2, and let me write 3 here, because once these assumptions that the Drude made while writing his model are clear to you, then you will appreciate everything afterwards. So, the third point that he made, this is a very interesting point actually, this is where the phenomenology comes in. So, he said that you see the electrons are bouncing off these ionic cores, right, but some of the electrons might go straight, they may not bounce off every ionic core, they might skip a few because they find a way in between the two ionic cores and so on and so forth. So, he said we have to define a quantity which is the average time between two successive collisions, average time on an average. Sometimes the electron will collide more frequently than that, sometimes less frequently than that, but we have to define an average time between two collision events that an electron undergo. Right? We are just fixing our attention on any one electron. So, you take this electron and you see, you follow its motion. So, it goes here, it bounces off here, then it bounces off here, then it bounces off here. So, you as you can imagine that this time will be less compared to, for instance, this time or this time, but you are defining an average time, tau. So, this is called tau. This is known as the relaxation time. So, relaxation time is the time between average time between two successive collisions that an electron suffers, right. So, if tau is the relaxation average time between two successive collisions, then what would 1 by tau be? Is the rate at which the collisions are happening, right. Average time between two successive collisions. So, 1 by tau will give you the rate of collision and the quantity dt, where dt is a time element. Dt by tau will give you the probability that the electron will suffer a collision in the time interval dt, right, the way we have defined. So, dt by tau is the probability of electron getting scattered in the time interval between t and t plus dt, all right. Probability of electron getting scattered in the time interval t to t plus dt. Now, of course, if this is the probability of electron getting scattered or probability that it will collide, then 1 minus this will be the probability that it will not scatter, it will not collide, it will just go unhindered. So, we will use that in building our theory. Now, the fourth point and the last one before we come to more details of a more formal way of writing the model. The fourth point of this model is that the that suppose you create a temperature gradient, suppose you start heating it here, then the electrons in this region will have more velocity or speed or whatever you want to call it. Now, but that heat will not remain localized here because it's a metal. Remember the kitchen experiment when you're cooking, you cannot touch the vessel even though only the bottom is getting heated. That heat travels from here to here. That heat travel happens through these collisions. So, collisions is the only way through which thermal equilibrium is reached. So, a thermal equilibrium is reached through collisions. So, the fast moving electrons, they collide with the slower moving electrons, give some of their energy to the slower moving electrons and so on and so forth. So the fourth point is that the thermal equilibrium in Drude's metal is achieved through the collisions. Now, this point may look slightly, counter to this point where we say we neglect the electron-electron interaction, right? So, here again, I mean the exact mechanism how it happens is not very important. The point is that when you have a situation like this where you heat one part, then the equilibrium is reached only because there are collisions, because besides collision there is nothing else that is happening. Otherwise, everything is just perfect. The ions are not moving, the electrons move of course, and they collide against the ionic cores. They may be colliding against each other also, and that is how they probably exchange energy, but all those collisions are kind of elastic. The total energy remains conserved. Now, let us try to write the model more formally. So, suppose this quantity P is the momentum of an electron, momentum per electron, but not just the momentum, this is the average momentum. So, I am not really writing the average sign here, but you should understand that I am talking about the average momentum. Which average? Time average momentum. So, this is the time averaged momentum per electron or of each electron. So, if I have not applied any force field, external force field, in the absence of any external force field, what would be the value of P? It has to be 0, right? Because there is no charge transport which is occurring inside the material, in the metal. There are electrons moving, but if you imagine a cross section here, so there will be as many electrons going from left to right as from right to left. There will be no transport. So, this quantity would be 0 in the absence of any force field, but we apply force fields. So, what kind of force fields do we apply? We apply electric field, right? How do we apply electric field? By connecting it to a voltmeter, isn't it so? What else do we do? We apply magnetic fields, isn't it? When we are doing Hall effect experiment, what do? We apply magnetic field. So, these are at least 2 fields that we apply, isn't it? We apply temperature gradient, right? So, here we will be, temperature gradient is a different thing. The externally applied fields that we have, I am going to call them as F, and they can be in general time varying. So, you can have a time varying force field. So, we call it force field. And in general, the structure of this force field would be so the charge of electron times the electric field that you have applied, plus the charge of electron times the force due to the magnetic field, which is V cross B, right? That is all that is there in this force field. Okay. And besides this, we don't really need to know anything further to proceed with. But before I proceed further, let me also clear a few more things, because otherwise you will get very lost. So this P is the average, time averaged momentum per electron. Now let's try to distinguish two things. So from this momentum, you will get a time averaged velocity, right? That is known as the drift velocity. In textbooks, you will see the word drift velocity. That drift velocity is the velocity that you get from here by dividing it by mass. All right, but then the drift velocity would be 0 in the absence of a force field. But it doesn't mean that the electrons are static. The electrons are all the time moving because of the thermal energy that they have. So we need to distinguish between these two velocities. So the electron has a velocity v naught when it is traveling between the two collisions, right? And then when you apply a force field, this v naught will remain, but on top of that you will superimpose that v naught with another velocity that comes because of the force field that you have applied, right? So that is why I said first you worry about the case where this is 0. When this is 0, then this quantity is 0, then the drift velocity is 0, but the actual velocity is not 0. The actual velocity is, let's say, v naught. So we are going to denote it by v naught. So this is the thermal velocity by virtue of thermal energy, right? And how will you calculate it? You can not calculate or estimate, give an estimate of it. So the estimate of it can be that half m v naught square is equal to 3 half kT, kBT. So that would be one estimate, quick estimate of v naught, right? The other estimate, of more accurate estimate, if you want to do, of v naught would be, you can write v naught square, or maybe like this, square of the average squared velocity, right? That you have studied in the kinetic theory of gases. So that is how much is that? That is 8 kBT by pi m. So in that context, the Drude's model is analogous to the kinetic theory of gases, right? So the electrons are these little molecules of your ideal gas, okay? Except that you have now ionic cores which are not there in the ideal gas. That is the difference. What else is the difference? In the kinetic theory of gases, you know that the gas is contained within a volume, volume. So that object in which you are enclosing the gas, that has walls, and the gas molecules are also colliding with the walls of this vessel, right? But in the case of metal, as I told you, the boundaries are very, very far away from the bulk, right? The number of electrons that live on the boundaries are very less. So for all practical purposes, for you, the boundaries are not very important. What is important is these immobile ionic cores that are important. So if you make an estimate, either using this at room temperature, what would you get for V naught? So you can plug in the numbers. The mass of electron is 9.1 into minus 31 kilograms. Kb, you know, temperature is 300 Kelvin. So just trust me, because I did it before coming here. This velocity will come out to be 10 to the power, what is your guess? Okay, so in CGS units, it's 10 to the power 7 centimeters per second. That's the thermal velocity of electrons in the electron gas, in the free electron gas, in Drude's model, right? Now let me surprise you, or let me tell you the reality. The reality is that the actual speed of electrons in a metal are at least 2 orders of magnitude higher than this. Now, I mean, because you are, smart students and you are already in your third year, fourth year, I can afford to talk to you like this, because otherwise I will be confusing the students, right? So, in fact, I am telling you that Drude's model will not work for this reason, because this velocity in real solids, in real metals, in copper for instance, this velocity is 10 to the power 9 centimeters per second. So, where does that come from? You are not going to change the temperature. So, that is why this module is very interesting, right? Just to keep your interest alive. So, right now you can forget about that. We will just go by this 10 to the power 7 centimeters per second.
There can be some extra degree of freedom, like derived to get it on the translation degree of freedom, when there can be lower degree of freedom by this
That will again add 3 by 2 maybe. So, your order of magnitude will not change, right? Something dramatic has to happen, and that is what you would learn, what dramatic thing happens. So, even you can estimate using this, you get the same order of magnitude, some modulo, some prefactor, right? That will be different. Fine. But the velocity that you will get from here, which is 0 right now because the force field is not there, but once you apply an electric field, suppose you are driving a current of 1 ampere through a wire, right? Then there is the electrons have acquired an average speed in the direction of the electric field. So, all that was happening is still happening, but on top of that, you have superimposed an average speed in the direction of the electric field, right? That speed, can you guess what is the magnitude of that speed? That average speed would be of the order of 10 to the power minus 2, minus 3 centimeters per second. It's that small. We will make an estimate of that. So, you see, I thought I should tell this straight away, because you might get a little bit confused between the two speeds or the two velocities that we are talking about. Oh, I shouldn't have rubbed this. So, now the question we are asking is that if P t is the momentum of an electron at any time t, what would it be at time t plus dt? The question we are asking is, what will be the momentum of this particle at time t plus dt? Of course, the answer depends on whether the particle will collide or not. If it collides, if it does not collide, then you know that the momentum at t plus dt is not the same, because now there is a force field. Because there is a force field, because there is a force acting on the particle, on the electron, so therefore the electron will accelerate between the two. So, the situation has changed now. We have applied a force field. So, between the two collisions, the electron accelerate because of the force field that you have applied, right? So, suppose you have n electrons. So, therefore, the total momentum before the collision is this much. Now, let us say that out of this n electrons, n is the number of electrons per unit volume, out of this n times dt by tau will suffer a collision. You remember what I had written here? Probability. They will suffer a collision. Okay. What happens immediately after the collision? After the collision, the electron comes out in an arbitrary direction. You cannot decide a priori that this will be the direction in which the electron will come out, right? And we are talking about a large number of electrons, right? So, if you take the vector sum of their velocities or the momenta immediately after the collision, what would it be? 0, because they have all suffered the collision, right? On the other hand, the fraction 1 minus dt times tau, this fraction has not suffered any collision. So, what would their momentum be at the time t plus dt? Their momentum at the time t plus dt would be their original momentum that they had plus the additional momentum that they have acquired because of the force field. Is that right? So you can simplify this. So this will get, you will get n times Pt and then plus F t dt, and then what else you will get? You will get a term here minus dt by tau Pt, and then you will also get one more term which will come from multiplying this, and this term will be of the order of dt square. All right. Now you see that these electrons have not contributed anything to the momentum at t plus dt, and these have, and this is their final momentum, right. So therefore, at time t plus dt, the total momentum of your system, total momentum is momentum per electron times the number of electrons. So n times p t plus dt is equal to this quantity. Isn't it so? Is this clear to everyone? I can stop here, take a brief pause. If you have any questions, ask me now. Is this clear? These have not gained any momentum over the time interval dt between t and t plus dt. Why? Because they suffered collision, and after the collision they moved in random directions. So the vector sum of their momenta will come out to be 0. This is the fraction that didn't suffer any collision, right? So they just continue moving, and since they continue moving, their net new momentum will be their original momentum times the momentum that they have acquired because of the force field, right? And that is equal to so the total momentum should be the sum of this and this, but since this is 0, so this is the momentum at time t plus dt. So you can cancel this term over here, and you can rearrange this. So you can bring this guy here, and you can divide both sides by dt, and you can neglect the terms that are of the order of dt square. So what you are going to get then is p t plus dt minus momentum at time t divided by dt is equal to f t and then minus p t by tau. Is that right? Now this is nothing but derivative of p with respect to t. This is dp dt, right? So therefore the equation that you have arrived at finally, which I am going to write here. So the equation that we have arrived at, which will describe the motion of these electrons in the presence of a force field, is this: dp dt is equal to f t minus pt divided by tau. Does it look familiar? If you don't have this part, it looks familiar. The change in momentum is equal to the external force. But you have an additional term. And what is this term? This is the damping. This is the damping term. This is the term which is holding the electrons back from accelerating. Isn't it so? Because if you have an electric field, the electron is experiencing a force E time E, and if there are no collisions, it will just go on accelerating. But that doesn't happen. It accelerates for a while, then it collides, okay, then after collision it moves in some other direction. So that other direction motion is superimposed by a motion in the direction of EE, right. So that's collision part, the collisions that are happening is incorporated or embedded in this term. So this term is the damping due to collisions. Now just 5 more minutes, and let me take a special case just to illustrate how beautifully this whole thing works. So let's take the case of a special case of a force field which is time independent and which is just given by minus E. A constant electric field that you have applied, let's say here. This is a constant electric field applied in the positive x direction, let's say. So then, in this case, what would be the value of dp dt? The dp dt term will be 0 because this is a steady state. There is no time variation in the force field. So the average momentum will not change with time. All right. So dp dt is 0 because it's a steady state. You have applied a constant field and you have left it there. Okay. So this is a steady state. dp dt is equal to 0. So you plug in there dp dt equal to 0, and and to make things simpler, let's come out of the vector notation. Let's assume that the electric field is applied along the x-axis. So your V naught is the thermal velocity. It has 3 components, x, y and z. But the force field has superimposed an additional average velocity along the x direction alone, isn't it? The force, the average, that is the average. So therefore, you get what? So what would you get? You will get 0 is equal to minus E minus P. Now I am throwing away the vector notation, tau. Right now you can rearrange them. You can bring this guy here, and so you'll get P equals E tau with a negative sign, and this negative sign is coming precisely because you have an electron sitting over here. Now you can write P as mv, right? So you can write this as mv. Now very careful, this V is not same as the V naught which I had written there. This is the additional, this is the superimposed V because of the force field. Right? You remember the time average of P is 0 when there is no force field. The time average of V is 0 when there is no force field. The time average of V is non-zero now because there is a force field which is EE. So this is the time average velocity. So the time average, so the total velocity will be V naught plus the velocity due to force field, but the time average of V naught will become 0. And so you are left with just the time average of this, right? So you can put this m down and you can do whatever, lot of other things. Okay. Now, in your conductor, you're passing a current I. What is the definition of current? Charge flowing per unit area, unit time, right? So suppose the cross-sectional area of this conductor is A, right? And the charges are moving inside the conductor with an average speed v, right? They are moving in the x direction with an average, drifting along the x direction with an average speed v, right? So therefore, the current I would be the charge density times A times v. So this is basically this much of charge minus E. This much of charge will go through any cross section of this material in unit time, isn't it so? So from here you can divide this by A and arrive at a very useful quantity called the current density J. Okay. So once again I have dropped the vector notation, but if you write this equation vectorially, then your J vector would be minus E coming from the charge of electron times N times the average direction of the velocity, and this would change from place to place inside the material, right? J can change in general, but in this case we are dealing with a simplified. So for V you can plug in those values from there. So if you do so, what will you get? So you will get J divided by minus En. So this will be J over minus En is equal to minus E tau by m, and you can take these guys up and you can rewrite it. So minus minus will get cancelled. So what you get is something like this: J equals Ne square tau by m multiplied by the electric field. And does it look familiar? Maybe it doesn't. If it doesn't, then let's put it in a more familiar form. One more minute. So I can rewrite that as E equals m over n E square tau times J. Is that right? Right? And for electric field, I can write electric field in terms of potential gradient that I have applied. So E is just V by L, where L is the length of the sample. Right? So this is V divided by L, or you can okay, V by L equals to this bracketed quantity, and you can write J as I by A. Right? Now you can take L over here. Okay? So what you get is V equals this bracketed quantity times L by A times R. Now this bracketed quantity is all constant, right? We don't know what the relaxation time is, but this is all but it is some number which is a constant for a material. M is the mass of electron, N is the density, E is the charge. So this is now in a more familiar form. This quantity is called the resistance of the material, right? So therefore this is your R, which is equal to rho times L over A, where rho is the bracketed quantity and inverse of rho is sigma. So therefore sigma is just this, the electric. So we have first task is done. You remember the first point on the board, electrical conductivity. So we have arrived at an expression for electrical conductivity. Now we have run short of time. Otherwise, I would have shown you, which I will definitely in the next lecture, how this compares with reality, how good it is. Is it really worth keeping, or should we throw away? With so many assumptions, will it still work? We have found the electrical conductivity, right? Of course, here is one parameter that we don't know, which is tau. So we will see that. All right, we'll stop here.